My name is Michal. I work at Defense, where we use BPF to observe the network traffic and write firewalls and detect the malicious traffic. I'm Wadolowski on GitHub, Discord, Twitter, and all the social media. And nowadays I mostly write Rust. I think I started writing Rust professionally 2 years ago, but I have huge background in C, Go, and Python before in my career. Well, in the previous talk there was a question like how many of you are system programmers, but I would like to see again, like how many people. All right, so BPF stands for Extended Berkeley Packet Filter, and at the beginning it was only about capturing network traffic and looking at packets and being able to write very small C programs which get the packet and decide whether it goes through or not. But nowadays it's more than that, and I would say that the most fair definition to use today is that it's a virtual machine with its own instruction set, which is able to run sandbox programs. And it came from the Linux kernel, but nowadays it's also coming to Windows. And there is also a blockchain project called Solana, which is using the technology for running smart contracts in that kind of virtual machine. But here in the context of the call, I'm going to talk only about Linux kernel. So the definition for Linux kernel is that it's a virtual machine which executes the code, which is triggered by the events in the Linux kernel, and in your code you can get the event and observe it or decide what's happening with it. And it's event-driven, and usually, for example, when you write a BPF program which is receiving a packet, you receive the memory, the pointer to that packet, and you can look into its content, you can modify it, you can drop it or let it go through. And there are many events which you can observe in BPF right now, but the most important ones, of course, are the network ones. And there are two types of programs, XDP and classifier. Classifier is very general. You can observe both ingress and egress traffic. And XDP is faster. It's like very XDP acts on the level of the network device driver, but for now it allows only ingress traffic filtering. So there are some limitations. But also the other feature of BPF is that you can observe the function calls. You can, for example, write a program which is triggered every time when some function in the Linux kernel is called and receive all the arguments or receive the return value of that function. So you can kind of like debug and trace the kernel by writing your own small programs. And you can also do it for user space, for uprobes. So if you have a binary which is exposing a symbol, you can also write a BPF program running in the kernel, which is attaching to that user space function, receiving arguments, and so you can also use BPF for debugging your user space binaries if you expose symbols. And also quite fresh feature, but it's working on the newest Ubuntu, for example. It's got introduced in kernel 5.7. You can write BPF programs which are attaching to LSM hooks. So, for example, if you are familiar with AppArmor or SLNX, now you can implement that kind of security. The security system is similar to those, just using BPF, and you can use the same LSM API to it, and many, many more. And well, the important difference between BPF programs and normal kernel modules is that BPF has a verifier, so it's a virtual machine, as I mentioned previously. So in BPF, it's very important that the kernel and that the verifier and the virtual machine are making sure that you are not accessing memory which you are not supposed to access, and that the BPF program doesn't panic the kernel, it doesn't crash the kernel. So it provides more security, because when you are writing like a regular kernel module, it can crash. In theory, eBPF program cannot crash. And when you are writing a BPF-based project, you usually split it into parts. There is eBPF program itself, which is loaded into the kernel, but then there is a user space process which does the loading and manages the life cycle of that BPF program. And also feeds the BPF programs with data. There is a concept of BPF maps, and that's pretty much like a storage for BPF programs, which is shared between user space and the kernel space. There are many kinds of them. There are almost like 20 kind of maps, but the most important ones are hash maps, arrays, and ring perf buffers. So in case of hash maps, it's just a KV store, which is shared between BPF programs and user space processes which loaded those BPF programs. And perf buffers are buffers in which you can push an event from the BPF program to the user space process. And usually it works that you define your own structure where everything is sized, and you write the data into that structure and push that structure into perf buffer. So it's, for example, to push a notification to the user space process that I received a packet, and and examples of BPF projects, the most popular ones are Cilium, which is Cilium is one of the most popular Kubernetes networking plugins, and there is also Tracy, which is application tracing tool, and Falco, which is a security tool. But yeah, the most of popular eBPF projects are written in Go in C. I mean, in the most of cases, especially Cilium, the user space part, which is loading and managing the BPF programs and also interacting with Kubernetes, is written in C, in Go, and BPF programs themselves are written in C. But yeah, in AI you can do everything in Rust, and there are already some projects which are doing everything in Rust. I mean, both BPF programs and user space part. There is BPFD, which is a project made by Red Hat, which is like a daemon for loading different network-related programs, network filters. So it's like a manager of different network policies based on XDP. And there is a project called Pulsar, which is an observability tool for IoT devices. So it's like a set of small BPF programs which are monitoring what's happening on Linux on IoT devices and are generating metrics based on that. And yeah, there are official libraries to use eBPF, and the first one, the eBPF, is completely based on C, so both user space and eBPF part are written in C. The later ones are introducing the other languages in the user space part, but the eBPF programs themselves are still written in C. Which is different in AI. In AI, everything is written in Rust, even eBPF programs. So Rust compiler is able to compile to BPF bytecode. That's because generating BPF bytecode is actually a feature of LLVM. So in theory, you could try to bring a support of compiling any language which has an LLVM frontend into BPF bytecode. But so far, the only frontends which support that are Clang for C and Rust C, thanks to which we can write BPF programs in Rust as well nowadays. And now I'm going to talk a bit about benefits of AI and why, in my opinion, it's nice to write BPF programs in Rust instead of C. But before that, there's a story about Rust and Linux kernel. So very recently, Linus Torvalds merged the pull request which introduces the support of writing kernel modules in Rust. It's going to be released in the kernel 6.1, which will come, it will be basically the next version of the Linux kernel. So starting from the next stable Linux kernel version, you'll be able to write kernel modules in Rust. But, well, since I mentioned that the difference between kernel modules and BPF is that BPF is more secure, and you have the verifier which takes care that you are not accessing the memory you shouldn't access, and that it's not crashing. There is also an initiative of rewriting some parts of kernel in BPF itself. And so far it's happening in C, but the point of AI is that you could do both. Like if you are rewriting some kernel-related functionality in the BPF, you can do it in Rust. And well, talking about benefits of writing BPF in Rust and IA, in next slides I'm going to talk about benefits, but people are often wondering, if I write BPF programs in Rust, they are probably more secure, right, in terms of memory, because there is borrow checker. Unfortunately, it's not the case. The most of BPF programs are receiving the pointers to the kernel memory or user space memory. So the most of the time you are dealing with the memory which isn't allocated by the borrow checker by Rust. But you are receiving the memory given you by the kernel, and accessing it is an unsafe operation. So from my experience, half of your BPF code is going to be unsafe. So so that's the remark that writing BPF programs in Rust has many benefits, but dealing with memory in BPF, you still need to rely on a BPF verifier and on the kernel, how they do that. Rust isn't saving you much with that. But the first benefit is type safety. So when you write a BPF program in C, C isn't as strongly typed as Rust. So here we have an example where we try to write an XDP program, which is the kind of program which lets you observe the packets on the network device driver level. But then we provide a wrong type of argument, because instead of providing the XDP context, we provide skbuf, which is related to networking, but you should use that argument in different types of networking programs. So instead of using XDPMD, we are using skbuf. And when you compile it with Clang, it compiles. There is no error whatsoever. And you are going to see the error after you try to load that program, actually, but compiling it is completely fine. But when you try to do the same mistake with Rust, so here we have the XDP macro, but then we try to use skbuf context. Rust compiler will complain because macros included in IA are strongly typed, so we make sure that you're using the proper types for proper type of BPF programs. The other thing that's very superficial, but error handling in C and especially in BPF is comparing integers all the time. And it's nice that when using AI and Rust, we can return a result. Of course, at the end, we need to wrap it in that kind of function where we match and return the integer, because that's what kernel is expecting. So at the end, the kernel is expecting the BPF program to return some integer status, but you can just wrap it and write your bigger logic in a function where you are actually returning the result enum and handle the errors with quotation marks and native Rust way. A very important thing, currently, when writing BPF in Rust, you cannot panic. We just don't allow it. So all the errors in your BPF programs have to be recoverable. So yeah, the principle is that if you write a BPF program in IA, you have a bigger function where you return result, and you make sure that everything is handled. And Rust toolchain is everything you need when you use IA. So we are not wrapping Clang in any way. There is no need to install Clang or like external LLVM. You just need to install Rust with Rust app, install few libraries, and you are ready to go. And we have also a logic library, which is a difference between writing BPF programs in C and Rust. In C, there is the official way in C to push to use logging is the BPF printkey macro, but it's not pushing those logs to the user space process, but it's pushing it to the kernel trace. So when you have multiple BPF programs running, the logs are getting mixed there. In IA, the approach we took is that our logging library is using perf buffers to push the logs straight to the user space process, which is managing the lifecycle of that BPF program. So for example, when you are writing some application which is running on Kubernetes, let's say, and is managing BPF programs, you are going to get all the logs from the kernel space to that user space process, and then when you do for kubectl log your application name, you are going to receive them there. So yeah, we just decided that the architecture where you are pushing all the logs to the user space process, which is owning the BPF program, is a better approach. And yeah, it looks like that when you, so that clone binary is a user space process which is loading a BPF program, observing the clone syscall in the Linux kernel. And every time our BPF program is observing that there is a new process created, it's pushing the logs straight to the user space process. We support async on the user space side, so yeah, user space part of the project can be asynchronous. We mostly support Tokyo, but there is also support of async STD, although less commonly used. And yeah, the steps to start with IA are, first of all, installing nightly. That's because BPF target is still tier 3 target in Rust C, so it's not stabilized. We are working on doing that, but for now you need Rust nightly to compile the BPF programs. Then you need to install BPF linker, which is our custom linker to link together the different BPF objects into the final BPF object. It's not done in LLD yet. There are ongoing patches to be able to do it with the official LLVM linker, but so far, yeah, we had to come up with the custom linker. And then the last thing you need is cargo generate to use the template of our project, because we provide the template. So it's easy to start, and when you try to generate the new AI-related project, you are prompted for what kind of program you would like to create and what project name, and yeah, then depending on the program type you choose, you might be prompted with some more questions, but at the end, you receive a simple example of the program which you can start modifying. And the project layout. Yeah, I mentioned before that usually BPF-related projects are divided into the user space part and eBPF part. Here we add also the common crate. So the purpose of common crate is to store some. If you need to have some types or structures which you share in between BPF part and user space part, it's very convenient for providing types you use in BPF maps, for example, then you are supposed to put them in the common crate. And yeah, the firewall crate is the user space crate, which is managing the life cycle of BPF program. Firewall eBPF is the BPF program itself, and it has the Rust toolchain TOM file, which is enforcing usage of Rust nightly there. And yeah, for convenience, we provide some Xtask commands for building the project. And yeah, those Xtask commands are, there is a Xtask run command which does everything, so it compiles all the parts of the projects and finally executes it. And we have an Xtask command for building the eBPF crate, because otherwise without this Xtask command you would need to write cargo plus nightly and provide all the arguments. That wouldn't be so convenient. So yeah, by default in IO template we just provide Xtask command for that. There is one huge thing missing in IA. So in BPF there is a concept of compile once, run everywhere, which is a mechanism to handle the differences in kernel structures in between kernel versions. So basically, BPF has its own debug type format called BTF, which stands for BPF type format. It's generated from dwarf. So basically what LLVM is usually doing is that it's converting the dwarf debug info into BTF. And one of the purposes of that is to be able to relocate the kernel structures when they differ in between kernel versions. That's not supported in IA yet. We need some more work there. But yeah, hopefully in some time, like let's say half a year, we will be there. So yeah, one remark, IA is, I would say, very ready to use when it comes to networking programs, because in networking programs, kernel structures don't change much. There is no chance that the definition of IP header or Ethernet header is going to change anyhow in the next 20 years. But if you are using something, some kernel features or some kernel structures which change in between recent kernel versions, then yeah, so far you still need to do stuff in C, and but hopefully we will get there. Okay, enough talking, and let's see some simple firewall written in IA in action. So here I have a quick demo. So yeah, let's try to access the IP address 101. For now we can do it. And we have a small BPF project which acts as a firewall and is supposed to block all the egress traffic going to 111. And as we see, it's working. So we have a log showing that the traffic going to 111 got blocked. And to show that's not a fake stuff, we can try to change the IP address to 8888. And see that that filtering is still working. And yeah, now when we try to ping 8888, yeah, it's not working, so our firewall works. And a bit of code example, maybe. Yeah, I still have a few minutes. So that's how the BPF crate looks like. So we have a definition of hash map, which is basically our hash map of IP addresses which we want to block. We store. Increase the font size a bit. All right. Yeah. So it's IPv4 only, so yeah, for convenience, I'm just using U32 for storing IPv4 addresses. I have a helper function for getting the packet headers from, because, well, here we receive the XDP context, which is like which contains the whole packet. And then we are using that ptr add helper to firstly get the Ethernet header, then get the IP header and get the value of the source IP address from IP header as other field. And then we are using the block IP function to check whether our IP address is in the block list, whether we are supposed to block it. If yes, we do XDP drop. If we allow it, we do XDP pass. And here we have the user space process. We initiate logging, and here we are loading the bytes of the BPF program. So the BPF program is like at the end kind of embedded into the user space binary. We initialize the logging of BPF. We get our program and load it and attach it to the network interface. And here we have the clap option for the network interface, which we want to listen on. And then we access the block list map. Oh my God. And add our IP address, which we want to block, to that block list. We insert it, and then everything is done, and we are just waiting for Control-C. And here the life cycle of the program ends with the scope of the main function. So once we press Control-C and the program exits, the life cycle of the BPF program ends and it stops working. That's why on the demo you could see that when I interrupted the user space process, the blocking didn't work anymore. It was allowed. There are options to extend the life cycle. If you want, you can get the link to the program and pin it in the BPF file system. There are ways to not make the life cycle of the program dependent on the scope of your function, but by default, your program is dropped when you go out of scope. Okay, I think that's everything I wanted to talk about. So, do you have any questions?
Thank you. Questions? Lots of questions. Does this work? I think he was first, then you, and then we go up.
Okay, thank you for your talk. It was very interesting. I wonder about the restrictions of the eBPF part of the program, because it runs in kernel, so obviously you need to use no STD, I guess.
Yeah.
But there will probably be other restrictions, like can you even use external crates? And the eBPF verifier, is it true that it needs to prove that the loops terminate at some point? And what about the size, if you include like lots of template-heavy code? Like, can you talk a bit about that?
Yes, so actually you can use crates without any external crates without any problems as long as they are no STD. So any no STD crate can be a dependency of eBPF crate. There is limitation of number of instructions, so one BPF program cannot have more than 1 million of instructions in BPF assembly. If your BPF programs are too complicated, you can split them and do so-called tail calls. So you can do up to 32 tail calls. So you can, at the end of one program, call the other program to keep doing the stuff. So in theory, like if you plan it properly, your limit is 32 million of instructions, but then you need to do those tail calls logic and what else? You cannot do too much loops, of course, so you need to make sure that when you make any loops that they are limited by some constant value, which the BPF verifier knows about. If it's some dynamic value, which BPF verifier is not sure how big is it, it will, of course, complain, because it will assume that, like there are infinite number of instructions to be done. So you need to be really careful that if you put any loops that you bound it to some constant value, which is not too big. And same also with accessing some memory. So you really need to make sure that you have some constants with the max size of stuff you're accessing.
Thank you.
Thank you. I think we already had a few. And who was on your side? You had a question? And then we can maybe fit a few in. Yeah.
Yeah. My question was, you say it was forbidden to those panicked, unhandled panic, and you how did you manage that in your library to forbid that?
Yeah, for now we just forbid to panic.
Okay.
So so when you write a BPF program, all the errors need to be recoverable. You cannot unwrap. You cannot panic directly. Yeah.
Well, what happens is compile error? Or?
Not compile error, but definitely verifier is going to complain.
Can the questions
but for compilation, I think that in examples we are explicitly doing here we have our panic handler unreachable unchecked. Yeah, but if you wouldn't have that, then it would fail later in the scope of running it and trying to run it in the kernel.
The first questioner had the brunt of my question, and the answer was really interesting. But I'm also curious when the eBPF verifier runs.
So it runs when loading the program. So it's basically in the kernel. It's part of the kernel JIT. So before kernel actually starts executing the program, it looks into the bytecode and has a set of rules what to look at.
And I'm just curious, if it doesn't rely on any runtime behavior, could it be moved into a compile time step?
I didn't think about it. Maybe it could, because it's basically, it's operating on the BPF bytecode, which is generated by LLVM. So in theory, it could be maybe moved to the compilation step before. But for now, it's the part of loading in the kernel. I'm wondering.
Would defeat the purpose of eBPF to prevent you can load anything into your kernel and you still cannot crash the kernel.
In that vision, I would say that verifier stays in the kernel, but we also have some step in LLVM to get compile time error. Because that's what you meant to have the step in where LLVM call already complains. That's an interesting idea, I think, but it's just not done, I think.
Thank you.
Maybe we have time for two more. You two, right? First you.
Yeah, so my question was also relating to panicking. So one of the main reasons why Linus wasn't really convinced of having Rust in the kernel is that Rust by default tends to panic rather than giving undefined behavior. So my question is, what if you actually, you don't call it unwrap, but you could still panic somehow, right? If you fail to allocate memory for your data structure or something, Rust can panic, and that's not caught at compilation time by the verifier, right?
If you fail with allocation on the stack, because in BPF you can only allocate on the stack, and the stack size is 512 bytes. Otherwise, if you want to allocate something bigger, you're supposed to use BPF maps, and then basically kernel is responsible for allocating the memory. So it's a very common case that you put some bigger buffers in maps if you want to store kilobytes of data, let's say. I don't know what to say. I never encountered such a problem that we would panic because of Rust being unable, having some issue with allocating something on the stack memory.
I'm not sure if that's still the case, but I was aware that that's the main reason why Rust wasn't allowed in the kernel, because it doesn't have kind of failable alternatives to what it provides as the default. Yeah,
right. I think Rust for Linux came with their own replacement for the alloc library because of that. So
exactly for that reason.
Yeah, so they are not using the standard alloc, they have their own. And yeah, here we are using the standard alloc library. Yeah, we never encountered such an issue, but
maybe it doesn't happen because you just restrict what the program can do, right? So you just don't allow to panic.
Also on the other hand, like when you write BPF programs in practice, you don't use that stack memory much. So like, especially here, we store just primitives in variables. So we have like let h proto, which is like U16. Like in BPF programs in practice, you never store bigger data than primitives. So that, like you allocate pretty much primitives on the stack. And when you have something bigger, it's like either coming from the kernel, then you have like a big chunk of memory coming in. Or when you want to allocate something bigger, then you create a map, you create your own structure with a buffer with like some U8 array. And then, yeah, it's on the kernel too.
But it could technically still panic after all.
It could, well, but it's then not Rust doing it, because then you are when you are creating a buffer in the BPF map in the kernel, then you have an unsafe operation of like instantiating a map, but it's then the kernel doing that, so it's not Rust itself like panicking.
Maybe it means like if you index into something that's out of bounds, but I guess Clippy will catch that if you forbid slice indexes or whatever.
So out of bounds is caught by verifier already. So it's BPF verifier catching like out of bounds error.
Maybe since we have panic handling.
I think there was one more question, and then that's about
Sorry, just curiosity about limitations of eBPF as a platform. About loops, I understand the verifier cannot be very smart, but at the cost of being not ergonomic, is it possible to just make a loop that is obviously bounded by a constant and actually managing early returns early, like with break by yourself? So the code of the loop is less ergonomic for the developer, but in practice the verifier says that is not going to exceed a constant, period.
I mean, yeah, if you define some constant which is fine for verifier, you can early return, yeah.
So you still have break as a statement, which means that you can, and at that point, is there a limit on the number of the iterations?
Yes, so if you have a break inside a for loop, verifier will still assume the number of instructions, which will be done without break.
So the number of instructions is the number of counted instructions at a time. So every loop counts for the length of the loop times the number of iterations. This is the 1 million.
Yeah.
Okay.
I mean, the whole program is supposed to have at max 1 million. So if your loop is in the middle of the longer program code, then
yeah. I understand.
But assuming, if we assume that your whole program would be kind of wrapped into that for loop function, you have some break inside it. But after that break, you still have some code which is executed when the condition for breaking doesn't happen. Then the verifier is going to assume all those operations happening after break, because it will assume the worst case scenario that the break condition never happens. So it will assume all those instruction and times.
And anyway, it is possible to create user data types like structs and put them as values in maps.
Yes, yeah.
And share them between the eBPF and the user space part.
Exactly. So I will quickly show one example. It's on my friend's GitHub. Sorry, I cannot type on Mac keyboard. So as I mentioned, like the common case in BPF is that if you want to store buffers bigger than 512 bytes, you can put the capacity, and then you have a structured buffer, for example, when you store bytes, and that buffer is stored in the map. But also the other example, maybe There is an old version of the firewall program I just showed, which didn't use IALog library yet. So for pushing out the events about some packet being blocked or accepted, it was actually using a common structure, and it was using the events perf event array. So it was pushing like the packet log structure, and the structure is defined in my app common, in the common crate. Yeah, here it is.
Okay.
Yeah, so you can
Thanks a lot.
define. I mean, as long as that structure contains primitives which are like fine for C and for the kernel, it's possible to do that.
Okay, thank you. What a nice ending to the meetup. Thank you, Michal.
Thank you for listening.